In this problem, we have a disk that has a velocity and acceleration as shown. So the disk is rolling, it's going forward at 5 meters per second, but accelerating backwards at 2 meters per second squared. So it's rolling on a horizontal surface without slip, and we want to determine the velocity and acceleration of points A, B, and C. All right, so we know something about the velocity and acceleration of the center of the disk. So we're going to define right as being positive x and left as being negative x. So the acceleration is in the negative x direction. We also know the radius of the disk. All right, so first we want to draw a figure, include the velocity directions, the IC, and a coordinate system. Because it rolls without slip, we do have an IC here between the ground and the disk. Then we're going to apply the relative velocity equations from any known point to any unknown point, and we'll repeat that for the acceleration. All right, so we have a figure. We know that the IC is at the ground because there's no slip. And then we also know that the velocity is perpendicular to the line that we draw from the IC to the point of interest. So you can see VA is perpendicular, VB is perpendicular, and VC is perpendicular. And the magnitude increases the longer this line is. So we would expect the magnitude of A to be larger than the magnitude of C, and the magnitude of C to be larger than the magnitude of B. All right, so our angular velocity is going to be clockwise, whereas the angular acceleration will be counterclockwise because of how the acceleration, the linear acceleration, is given. All right, the disk rolls without slip, so that means that the velocity of the center is r omega. So we can say that for any disk or wheel that does not slip. All right, we know what the velocity of the center is, we know what the radius is, so we can solve for omega. All right, once we have omega, then we can go from any 2 points in the disk. So we're going to go from the known point O, the center of the disk, out to A. We could also go from IC to A, but that would be a little more complex as far as breaking down the radius. All right, so O to A. We're going to do VO plus omega cross R A relative to O. Okay, so VO, omega, we're assuming to be clockwise, so that's negative K. And then R we will break down into the X and Y components, so cosine minus I, sine positive J. And then we take the cross product, so minus K cross minus I is J, minus K cross J is I. All right, we plug in what we know and we get the velocity of A. All right, we can do that for point B as well. In this case, the RB relative to O is fairly simple. It's just 0.3 in the X. So you see that equation, take the cross product, and we get the velocity for B. And we can do the same for C. So we could go from the IC or we could go from O, but O is easier because it's just 0.6 in the I to get to C from O. So we take the cross product and we get a value. So once you get the value for the velocity, double check with your directions. So does C look like it's going down at a 45-degree angle, which the velocity says it should? Yes, it does. And for B, does the X component look more than the Y component? Yes, it does. All right, then we can go on to the acceleration. Similarly with the acceleration, if the disk is not slipping, then the acceleration is r alpha, so we can solve for alpha. Then we can go from O, a known point of acceleration, to A, which is an unknown point. So we apply the relative acceleration equation. We've assumed that alpha is in the k direction, so we just decompose r into the I and j, and then we put the minus omega squared r on as well. We take the cross product and we get a value for A. All right, we do the same for B and the same for C. So make sure you look over all the cross products and the relative positions.